All right. So my name's Casey Stella. Thank you guys for coming out, guys and gals. Really appreciate you guys coming to hear me talk. What we're going to be talking today about is natural language processing on structured data for structured data investigation on actually non-textual data. So I know I kind of it's sort of the bait and switch. You see NLP and you think we're going to be talking about analyzing tweets, and it's not at all about analyzing tweets. But it's actually something I think is cool of borrowing from some NLP techniques, some techniques for unstructured data analysis from NLP to use on structured data. Anyway, I'm getting ahead of myself. So first, who am I? So I'm a principal architect at Hortonworks, and I focus on data science. So I'm in the consulting division. I work day to day with clients, actually doing data science for them. So I primarily work in the Hadoop ecosystem, and I have for a few years now. So before this, I was doing data analysis and data mining at a startup that was spun out of the Cleveland Clinic. It was recently acquired by IBM called Explorus. We were doing clinical data mining. So you go into the hospital, we look at your records, we help the doctors know and the hospitals know how well they actually are performing healthcare for you. So it's kind of a win-win. Hospitals get analytics, we get money, and you guys get insights. So win-win-win all the way around. Before that, I putted around various startups, but I did signal processing on seismic data at Ion Geophysical, which was in the oil industry. And I was a math grad student way back when in theoretical CS. All right, so domain challenges in data science. So data scientists have to merge analytical skills with domain expertise. I get dropped into clients. So if you see from my background, there's a lot of different domains there, and it's sort of expected that data scientists are able to kind of be dropped in and understand a domain quickly, and that's challenging, right? There's a lot of ways to understand a domain. One of them is to simply sit down and read. One of them is to talk to experts. But the problem with talking to experts, as I found with, especially in clinical data, in seismic data, you talk to experts, and the experts are electrical engineers or scientists, right? Physicists in particular, and they generally know what's up. You talk to doctors, and they come with a lot of tribal knowledge and a lot of, not to say intuition, but it's not exactly, they come with their own biases, right? And that's good and it's bad. It's good to understand the biases, but it's also very good to understand what the data is telling you. And that's where unsupervised machine learning techniques can be extremely useful for sussing out what the underlying structure of the data without relying on people with their own foibles and biases, right? And also, especially if the data is complexly related. So we're going to borrow some unstructured, unsupervised structured learning from NLP actually and apply it to the domain of clinical data. Well, one challenge. Well, first we'll talk about the technique. So I'm sure most of you have heard of word Tyvek. It's relatively famous at this point. The Google guys are good at what they do. It's a vectorization, in the off chance that you haven't, it's a vectorization model created by Google that attempts to learn the relationships between words automatically. So this is things like finding similar words. So it's changing a problem of language into a problem of linear algebra or computer science, right? It uses a neural network to learn vector representations, and there are a couple ways to do that. Recent work I think that's kind of interesting, and I would urge you to look at the link that I have down at the bottom. There was recent work by some of the guys at, I believe, Stanford at this point. Yeah, I think Soker and Manning are at Stanford, so right down the road, showing that the word Tyvek model is actually equivalent to a weighted word co-occurrence. It's finding the connection between word co-occurrence and this extremely complex neural network, skip-gram model. but it actually turns out into, it turns out it translates, what the neural network is learning is essentially a riff on word co-occurrence, right? Which is kind of intuitively nice, because that's what we were doing, forever and a day ago about, the old bag of words model. It's enhanced and better, but it still links back. So it's nice and intuitive. It's not this black box, in other words. Actually, I'll digress briefly. One of the reasons why I say that is it's important to understand how to explain techniques to clients if you're doing data science in a day-to-day life, because you have to talk. Your audience is often executives who don't know, haven't been in a calculus class in a long time, much less have ever heard of deep learning in any way other than maybe a blurb in Fortune magazine. So it's important to be able to explain this in a reasonable way. So I often find ways to connect with to connect complex techniques into intuitive language, I guess. All right, so clinical data. So clinical data is really rich and really cool, and probably very few people get to play with it because of HIPAA and regulatory requirements and things like that. But it is super cool. It really is. So when you go into the doctor, the doctor will generally take your vitals, right? They'll take your pulse, take your blood pressure, etc. Labs are performed. They'll measure, they'll draw your blood. They'll measure HbA1c if they think there's a problem with diabetes. They'll measure your blood glucose level if they think there's a problem with sugar, cholesterol, etc., etc. Right? All those things that Dr. Oz talks about so much. Procedures are performed if something needs to happen. Diagnoses are made, right, after the labs and all the things are done, and drugs are prescribed. Right? This can be seen as so each of these things can be seen as a clinical word, and the entire encounter can be seen as a clinical sentence with some structure inherent into it, right? So the idea, the hypothesis, is that you can use the structure like you use any other natural language sentence, and you can use the techniques of Word2Vec to find the connections between each of these clinical words. So find the most related diagnoses by looking at diagnoses that were used in a similar way, in the same context, in a similar context, right? Okay. So one of the challenges is actually finding data, right? Very few people have, just a bunch of very personal clinical data just bouncing around the internet, at least not that one can use with any sort of ethics. But it turns out there was an electronic medical records system that was looking to predict people who had diabetes. So they depersonalized 10,000 patient records, 10,000 patient encounters, I should say, more records, and put them out as part of the Kaggle competition. And I ingested and pre-processed this in Hadoop. It's a small amount of data, but if anyone is dealing with medical data, you understand that most insurance companies, most hospitals have actually a lot of data. So it does fit very well within Hadoop. So I ingested the data and transformed it using Pig and Hive. Hive to store the actual records, and Pig to do the ETL to transform them into sentences and to normalize them, kind of scrub some of the bad data. Because the other thing you'll find out in healthcare data is it's extremely noisy. So that's about 80% of the actual problem. Okay, so if you're interested in the Kaggle competition, it's from 2012, and the link is at the bottom. This deck will be available after. Okay, so. Okay. That looks terrible. Hold on. Oops. Okay, so kind of as a preview for my talk at Summit, if you guys are attending, I have recently become interested in using notebooks for data science. I know this is not new, but in particular notebooks integrating with Hadoop for doing some data science. So what I decided to do is I was going to use the Python bindings for Spark, because Spark as of 1.2 has a very nice Word2Vec implementation right there available. And I have these nice sentences just itching to be analyzed using Word2Vec. So it's actually quite easy to do. Most of the work was in the ETL. I can pull the information from a text file, and the rest of this are nice little Python functions to pretty print the results and to find the nearest neighbors. Right, easy peasy. So one of the things I wanted to find, I wanted to figure out if we could do one or two things. So the methodology to determine if my hypothesis was correct, then that we could extract these these structured connection from these clinical sentences, these clinical encounters, is can I recover things that we know about from the domain of medicine, and can I see if I can find something novel? So if I find a bunch of stuff that's obviously wrong, or if I can't find the obvious connections, then you're not going to believe me whenever I find something not obvious, right? So atherosclerosis of the aorta, that's a big one, right? Tons of people are dying of heart disease all day, every day. Hardening of arteries. It's a terrible, terrible thing. So if you've ever worked in the medical industry, this is what's called an ICD-9 code. It's a diagnosis code. So what I'm finding is I'm finding the closest clinical synonyms to atherosclerosis. And you see the first one right at the top is peptic ulcers. So we've known this connection since the 60s, probably before actually. The earliest I could find was an editorial in the British Medical Journal way back in the 1970s saying that this was known. So it was known in the 1970s and part of the lore. So that you could see that this is actually, a strong connection. We know this, and it bubbles right at the top. So we're feeling pretty confident about the technique. This is good. So the first few are about peptic ulcers. The other diagnoses around peptic ulcers. There was one that was kind of interesting, was this one. Sensorineural hearing loss, unspecified. So what that is hearing loss. So why would hearing loss be connected to atherosclerosis? So this is one of the recent connections we found in 2012. So a quote from an article in the Journal of Atherosclerosis saying sensorineural hearing loss seemed to be associated with vascular endothelial dysfunction and an increased cardiovascular risk. So you see that hearing loss and cardiovascular risk are strongly connected, and you do see that in the data borne out. We found that in 2012. We found that from 10,000 patient records that were open sourced in 5 minutes on my laptop. Actually, took less than 5 minutes. That's kind of neat, I think. Knee joint replacements. So some of these things are, you're diving into the correlation category. Old people often have atherosclerosis, and they often get knee joint replacements. But you see that it does find that connection, which is right here. So yeah, it is finding that it's finding the things that we obviously know, and it's finding the things that were not necessarily as obvious, which is nice. One thing I thought, so the next one I wanted to look at was Crohn's disease. This is a common one. It's not necessarily just from the elderly. I wanted to kind of avoid, everyone really focuses on diseases of the elderly. Kind of wanted to focus on something that might happen to people who are younger. Crohn's disease is an inflammatory bowel disease and is fairly common. It's caused by a combination of environmental, immune, and bacterial factors. I thought this was kind of neat. So one thing that it found was the first one, the top one, is chronic gouty arthropathy. So arthropathy is arthritis, right? It finds a connection between Crohn's and arthritis. Arthritis is the most common comorbidity with Crohn's. So it finds the thing at it bubbles right to the top, the thing that is the most connected with Crohn's. The thing that I found that was interesting was the second most strongly connected is a abscess of the teeth. So a dental abscess is connected with Crohn's. And I thought to myself, that's very strange. Why would Crohn's have a connection with dentistry and your mouth. And if you think about it, your alimentary canal, the top of your gastrointestinal system starts at your mouth. So if you have inflammatory bowel disease and it has issues with your with the entire gastrointestinal system, and it bubbles into the mouth. Actually, it does connect to the mouth, and that is, you can see that if you look in the Crohn's forums with people who were suffering from Crohn's, you see a lot of discussion about dental abscesses. You don't see a lot in the literature. So this is something that I don't think is as known in the literature, but is seen in the real life, I guess, if you're to take internet forums to be real life, which you probably shouldn't. And finally, I think the most interesting one was this one. That is yeast infections. There is a strong connection between yeast infections. In particular, there is some belief amongst researchers that the immune response to yeast infections is one of the causes of Crohn's disease. And we found this out relatively recently. I believe this was from 2014. So it's still being researched, but this is the first time that they're really taking this connection seriously, and you see it bubble right to the top in finding these connections with the data. So the other thing that's kind of nice about this model is that it's not just about matching diagnoses to diagnoses. You can also cross-match different types of clinical words. So in this situation, I want to find the most associated drugs with HIV/AIDS, right? And so you see right at the top the triple cocktail. So that's a common cocktail of drugs given to HIV patients to prevent them from getting AIDS. And the second one you see is peroxide, topical peroxide. Same thing you use to bleach your hair, if you're into that sort of thing. The reason why is it is used to treat skin so the connection is there are the topical emollients are used to help soothe the skin, and in particular, peroxide has helped to dry the skin out slightly as a result of some of the side effects of the HIV medication. And you see that throughout the HIV forums as well. So the point here was to show kind of a few vignettes of some data investigation, finding the connections in this unstructured data using very simple techniques that is not in the domain of really data mining that most people think of. And that's really, yeah, right there. Any questions?
So in this example you just provided,
yes,
the connection you found out
yes,
for each of the disease, was there any particular ordering of those connections? Were you able to find out the significance of different connections?
Yeah, so that's a good question. So I'll repeat it. So the question was, is there any significance to the, you tell me if I'm being honest here, is there any significance to the rankings? Is one more connected than the other? And this is cosine similarity, so it's really, I mean, the way to interpret it is there's a vector and it is disconnected. The closer it is to 1, the closer it is to fully connected. The closer it is to 0, the closer it is to not connected. It's cosine similarity. Now, are there cutoffs, and do those cutoffs mean something? I have not found anything that I would really, so I would say anything above, from just looking at the data, anything above a 0.7 was a fairly strong connection. Anything below a 0.7 looked kind of bad. If you're dealing with one clinical, with one word if you're comparing diagnoses to diagnoses, when you're comparing diagnoses to other kinds of clinical words like drugs, you'll have to go a little bit farther out. Something like 0.5 to 0.3 was a strong connection, I would say. But that's, again, you know, kind of looking at the data and rule of thumb kind of thing, unfortunately. Yeah. I wish I had a better principled answer for you. Yeah. Well, actually, it's a funny. I've actually solved this problem as part of a team at client sites, and it was a riff on TF-IDF with a custom IDF function that was not your normal IDF function. And it found the connections just the same, right? It's the same kind of thing. And it's, again, it's a riff on NLP techniques, which kind of belies my background probably, so sorry about that. If I were being honest, probably another principled approach to this, and what I probably should have done, and what I want to do, is look at just plain correlation, right? What are the most correlated, right? And just in terms of, that would also give some insight. But this is at least the TF-IDF model did do better than simple correlation, and I suspect this actually will do better than simple correlation as well. Yes?
The connection with NLP is the context, the notion that a certain word is embedded in a local context that's more important than the overall document, right? So that weighting that you mentioned in one slide, maybe you said that, but I missed it. What was the notion of that context? So
yeah.
For words, is words that are near in the text,
yep.
right?
So the context is actually temporal. And you often have these things in order, right? When you go to the doctor, you get certain things in order. You generally get seen first. You have a vital, right? Your vitals are taken, and then there's either there are labs ordered, a diagnosis made, and these things happen, in the course of time for an entire encounter, right? So that it sort of forms it. You can think of it as forming a grammar in and of itself, right? These things are connected together. You really have to have the lab. You have to have the lab before you really have the diagnosis and things like that. That's the hope that you'll find the interconnections there.
The order in text is mapped to an order, a temporal order of in which these things have happened.
That's right.
And how about the length of this context? Is it like
yeah.
based on timestamps, or you go like 5 events in the past and 5 in the future?
So the way that the word Tyvek implementation works is part of MLLib, which is what I used. You can specify a window, and the default window is 5. And for the most part, that worked out fairly well. I did tinker around with the windows. 5 seemed to work the best. So the way that I did that, again, was kind of rule of thumb, right? I tinkered around with it. I said, this looked good. This gave me good results. This gave me bad results, because I could actually Google these things and find the connections. I had an objective function to kind of optimize, right? As long as atherosclerosis was bubbling peptic ulcers up to the top, I was pretty happy with the results, right? And then I could.
If you could do something more based on the timestamp, so you say like a month before and after.
Oh, it's for an encounter. So an encounter is they're split into episodes, right? When you go to the doctor, and you have this diagnosis, it is an encounter. It is distinct from the separate encounter that is already split up. There are clinical meanings for that. It is the notion of sentence associates with the notion of an encounter, which is a set of clinical words or clinical occurrences, if you will. Yeah.
So if I push the metaphor of language of
Please
NLP
do.
to the limit, then basically you build stories.
Yes.
And certain illnesses, the probability, because you'll have template of a story. The
Yes.
same like the stupid novels, whatever, are written, within.
Yes.
So, and then the implication would be, or is, if I just make sure that I got it, is, okay, the beginning of this story looks similar to this chunk of stories, therefore let me rush that because I know the end. That's the implication?
More like the word that you're using in this story is used similarly in other kinds of stories. So this word is associated with this other word in these other stories because they're used in the same way, so they probably mean the same thing. Now what you're talking about would be running what's called Tyvek, which is a vectorization of a document, which is very interesting, I think, and I haven't done that yet, and I do intend on doing it. So that would be, you take an encounter and you find similar encounters to that. So you have the notion of maybe a good encounter, or maybe a bad encounter, and you could find, or maybe a diabetic encounter, or an encounter, so you can know before you go in, maybe early, that you're likely to have diabetes because you've had these series of encounters leading up, right? That would be an interesting extension to this. This is just kind of the bare bones. These are words, are the individual clinical words, the synonyms and the analogies. The other thing that Tyvek does is actually analogy. Right? Because you're in a vector space, you can do things like king minus male Was it king minus male plus female is a similar vector to queen, right? So you can do these same kinds of things with these clinical words. You can take this diagnosis, subtract this diagnosis, and maybe see if there's a connection between these other diagnoses, like type 2 diabetes minus some very, very important comorbidity of type 2 diabetes. Is it similar to type 1 diabetes? The reason why I didn't do that is I couldn't find a real world use case for that one other than just it's neat to do. But at any rate, any other questions? Yeah.
Can you tell us a bit more about the metric you use to tune your model?
Yeah, so so here's one challenge with the Tyvek implementation for MLLib is you're bound to a cosine similarity, unfortunately. So the training and all of that business, it's unsupervised, sort of happens under the hood, and you kind of have to fit. You kind of have to live with their vector space that they create. The tuning parameters that you really have are window length. So like I said, basically it was kind of hand coded. I knew it was going to be somewhere between, it was sort of a hand grid search, right? I knew it was going to be somewhere between 3 and 5 because that made the most sense, because these clinical encounters were only, I mean, some of them were only 5 long, right? So that it didn't make sense to go more than 5. Actually, a lot of them were only 5 long. So a lot of the ways that you tune it is looking at your data and figuring out what kind of makes sense, and then running it a few times to see you have to pick an objective function to maximize. In this situation, it was very much a qualitative objective function. Do I still recover the things that I know are connections in the data, right, from a set of diagnoses and a set of drugs? And as long as I did, I picked the set of parameters that fit the best. But I know it's kind of a loosey-goosey methodology, but you didn't have very many levers to pull, as it were. Any other questions? Yeah.
Besides the keywords, have you taken a look at the key phrases?
Yeah. So I didn't. So you mean are these bigrams, essentially clinical bigrams, are these connected? No, I didn't do that yet. It's an interesting question. It is. One challenge about that is it's hard to interpret, right? It's easy to, if I go to a doctor and I say, hey, do you want to know all the diagnoses that connect to atherosclerosis? And the doctor says, absolutely, that's what they taught me in medical school. Well, this is what the computer thinks it is. But do you want to know all the diagnoses pairs that connect to atherosclerosis and gouty and gout? And they're going to be like, maybe. That might be useful for me. Yeah. Actually, because you were first, yeah.
So do you see this useful in sort of identifying the really rare things, right? Like, because obviously, this isn't going to replace a doctor. Right?
Nope.
And fundamentally, this is, as you point out, similar to what they learn in medical school, right? Like,
yep.
What diagnosis is similar, like, what symptoms lead to what diagnosis? So is the idea that you take this and then, as you say, combine multiple pairings of these models such that you can isolate the things that are rare, so like the sort of unexpected combinations that they don't explicitly learn?
Here's what I would like to see, because it's out of 10,000 patient encounters, you start finding things that we only found in 2012, 2013. I would like to see a much larger corpus run on this and fed into the medical research establishment to say, hey, are there connections between these things, to kind of seed the research. These are the things that the computer thinks are connected. Find a causal relationship between them as best you can. That's what I would love to see, in terms of a dream connection. Problem is there are very few people with that much data, and there are very few people with that much data with the willingness to do pure research often, right? At any rate, that's what I would like. I do not see this. This is not Watson in a box, right? It's not Watson on my Mac in Spark, but it does find connections in the data. The other thing I would like to say is this is temporal data, right? It's just temporal connections with some sort of grammar associated with it. You see this all over the place, right? In automatically mining the connections between data and relational databases would also work with this. If you can form a sequence of things with a grammar around it, or even with a grammar that you don't entirely understand, you can use this kind of thing by forming it into sentences and and borrowing from the techniques of NLP. It will be very useful. That's one of the benefits of Hadoop, is that you're not. I mean, you can start doing these sort of this unstructured data, this semi-structured data analysis, right? That's probably enough time of questions. You guys can ask after.
Let's thank Casey again.
Thank you.